Hi everyone, I'm Adrian from the Australian Computing Museum, or the ACMS, based here in Sydney, New South Wales, Australia. At the ACMS, we have one of the largest digital equipment corporation collections anywhere in the world. We were founded in 1994 by many people, including Max Burnett, one of the first employees of Digital Australia. DEC was founded in 1957 in Maynard, Massachusetts, and grew to be one of the largest computing companies in the world. In our collection, we have a significant amount of documents, computers, and training material. And today, we're going to present some of that training material to you in the form of old VHS tapes. So, please sit back, relax, and enjoy. Thank you.
As mentioned in the last unit, the process is the basic scheduling entity in VMS. Scheduling of processes is necessary because VMS is a multi-programming environment in which a number of processes compete for control of the CPU. In this unit, we'll focus on how VMS determines which process is scheduled for execution. This unit consists of one lesson. In it, we'll review the concepts of multi-programming and process states from earlier units, and then examine system events. Next, we'll examine the scheduling of time-critical and normal processes, and the role of hardware and software PCBs in scheduling.
VMS is designed for a multi-programming environment. The goal of a multi-programming environment is to efficiently use system resources, such as the CPU and memory. With multi-programming, there are several user images resident in main memory at once. Only one image at a time can execute. However, if this currently executing image passes into a wait state, there are several other images the operating system can select to execute next. A multi-programming operating system tries to obtain the right balance between compute-bound images and I/O-bound images so that the system resources, especially the CPU, are fully utilized. How does a multi-programming operating system achieve this efficiency? It uses a scheduler, a mechanism which allows the operating system to optimally use the CPU resource. The scheduler is a software interrupt service routine invoked at interrupt level 3. Let's take a closer look at the functions performed by a scheduler. The scheduler divides available CPU time among processes. In VMS, a process is scheduled rather than an image or program. A major goal of a scheduler is to implement an equitable scheme for sharing processor time. To do this, the scheduler selects processes for execution. It provides a method for more important processes to interrupt less important processes. Typically, some processes running on a computer system will have a higher priority than other processes. The scheduler also decides how long each process executes. It generally rotates the control of the CPU among processes so that all processes receive frequent and equitable chances to complete their computing requirements. To optimize the use of the CPU, the scheduler allows compute and I/O operations to overlap. For example, if a process must wait for an I/O completion, another process is allowed to run. Now, let's see how the VMS scheduler performs these functions. To understand how processes are scheduled, let's recall the three-state model presented in Unit 1. A process may be in one of three states: current, wait, or computable. You should note that throughout the rest of this unit, we'll abbreviate the words current and computable as shown here. The current process is the one which is executing. It is in control of the CPU. In a single CPU system, there can only be one current process. A process leaves the current state either by going into a wait state or by going back to the computable state. A process stops executing because a more important process is ready to run, because the process's time is up, or because it's waiting for an event. The wait state is one in which the process is waiting for some external event to occur. Actually, there are a number of wait states, each one defined by the type of event a process is waiting for. The state of each process is displayed when you enter the DCL command, show system. A couple of wait states are shown here. LEF means the process is waiting for a local event flag to be set. In most cases, this indicates the process is waiting for the completion of an I/O operation. HIB indicates that the hibernate system service has been invoked. This means that the process will be in a dormant condition until a wake request is issued. Your course reference guide contains a list of wait states, including many not displayed here. The third state is referred to as the computable state. In this state, the process is ready to execute and is waiting for the CPU. The scheduler only looks at computable processes to determine which ones are eligible to be current. To be more accurate, a process must be memory resident and computable to be scheduled to execute. Some computable processes are swapped out of memory to disk storage because there's not enough space to fit all processes in main memory. These out-swapped processes can't be scheduled to execute because they are not memory resident. We'll discuss how processes are swapped in and out of memory in the next unit. System events cause processes to move from one state to another. Simply put, a system event is any event that affects the ability of a process to execute. For instance, they can cause a process to become computable, representing a release from some wait state. Some examples of system events are an event flag setting, such as one caused by an I/O completion, an AST delivery, or a hibernate wake request. System events which impact a process state are generally reported to the scheduler via the Report System Event, or RSE code. When system events occur, the RSE code executes to find out what system event occurred and what to do about it. If the system event results in a change of state, the state of the process is changed. RSE requests the scheduler if three conditions are met by the process. In order for the scheduler to be invoked, the process must be 1. Computable, 2. Memory resident, and 3. The process must have a priority greater than or equal to that of the currently executing process. By checking the condition of the process, RSE avoids invoking the scheduler when the process has no chance of gaining control of the CPU. In scheduling processes, the state of the process is one of the factors the VMS scheduler considers. A process must be computable and memory resident in order to be scheduled. However, scheduling is also based on priority. VMS uses software priority levels as the mechanism to determine which process is the most important. The process defined by VMS to be the most important gains control of the CPU. There are 32 software priority levels used by the scheduler, numbered 0 through 31. Simply put, the process with the highest priority level executes first. At each priority level, processes are grouped into queues. A queue is simply a waiting line like that at a supermarket checkout counter. The first one in is also the first one out. There are 32 queues, one for each software priority level. Some of the queues, of course, may be empty. These 32 priority queues correspond to the memory resident computable process state that we discussed earlier. That is, any process in one of these queues is ready to execute whenever the scheduler decides to let it run. The software priority levels are divided into two groups of 16 priorities each. The upper 16 levels are called time-critical and are used for processes which must respond to events very quickly. Processes at these priorities are referred to as real-time processes. An example of a real-time process is one which is responsible for monitoring a chemical manufacturing plant. This activity is a time-critical activity whose delay might cause the plant to malfunction. The lower 16 levels are called normal or non-time critical and are used for time sharing and batch jobs. Both normal and time critical levels are subject to priority scheduling. That is, the computable process with the highest priority is the one that executes. Here, a process at priority 8 is executing. However, the executing process is preempted if another process with a higher priority becomes computable and the scheduler awards control of the CPU to the higher priority process. You can think of a process being preempted as being similar to network television programs that are preempted. Programming people at a network preempt programs when they judge the special program to be more important than the normal programming. For example, a program may be preempted by a breaking news story. When the special report is over, normal programming resumes. In a similar manner, processes that are preempted eventually regain control of the CPU. The operation of the priority queues is straightforward. A process at the head of the highest priority queue is scheduled to run until it completes, issues an I/O request, or is preempted. If the process is preempted, it returns to the end of its queue. If the currently executing process, in this case process B, issues an I/O request, it goes to a wait queue elsewhere in the system. After the I/O event for which the process is waiting occurs, the process is returned to the end of a priority queue. In the case of a time-critical process, the process is returned to the end of the queue from which it came. There is a resulting round-robin effect because processes always return to the end of a queue. This way, no process at a given level can monopolize the CPU. After all, if one of these processes were more important than the others, it would be at a higher priority level. At time-critical priority levels, the round-robin action is achieved strictly by returning a process to the end of the queue. At normal priority levels, however, time quanta are used to give each process a fixed time slice, or quantum. Let's take a closer look at the use of time quanta. Suppose there are 3 memory-resident computable processes at priority level 4. Process A is at the head of its queue, so the scheduler gives it control of the CPU, and process A starts to use its quantum, or time slice. If process A makes no I/O or system service calls, it is allowed to run until the moment its time slice is exhausted. At this point, another process is ready to gain control of the CPU. Here, process B is executing its quantum, or time slice. It controls the CPU until its time slice is exhausted. At this moment, process C is given its turn to run. In this case, while process C is still in its time slice, it issues an I/O request and goes into the wait state. Once again, it is process A's turn to execute, so process A takes control of the processor. With time-sliced round-robin scheduling, each user process is granted for a fixed amount of CPU time on a rotating basis. In so doing, VMS gives each individual the illusion of having a single user system and can thus service many interactive users simultaneously. Even with time slicing, interactive terminal users could potentially experience slow response time. I/O-bound processes run into 2 major problems. First, the I/O-bound process is often in a wait state. Each time the process gains control of the CPU and it issues an I/O request, its execution is interrupted. Second, the execution of the process is further delayed because it is put at the end of its queue when it returns from the wait state. If the operating system did not address these issues, the result would be excruciatingly slow service to the interactive user. To overcome these potential problems, VMS employs a scheme called priority boosting. Priority boosting is used only for normal processes, those processes with a priority from 0 to 15. With priority boosting, as soon as the I/O operation of a normal process is complete, the process is temporarily boosted to a higher priority level. For example, a process might be boosted 4 priority levels. The promoted process obviously gains because it runs sooner than it would otherwise. And if it's an interactive process, the terminal user gets a corresponding improvement in response time. What does it cost the processes on an intervening priority level to have an I/O-bound process promoted? Not as much as you might think. Once the I/O-bound process gets the CPU, it's likely to issue another I/O request soon. Therefore, the promoted I/O-bound process does not monopolize the CPU. Further, a process that does not get its priority promoted is one that does not do very much I/O, that is, a compute-bound process. Since a compute-bound process doesn't communicate with the outside world very often, it doesn't matter if it is slightly delayed, because no one's waiting for a quick response from it. Thus, through priority boosting, VMS is better able to service I/O-bound processes often associated with interactive terminal users. You should be aware of several things in relation to priority boosting. Every process has a base priority level. This level is typically assigned by the system manager when a user's account is set up. The boost occurs when the process's I/O completion occurs. In this way, the system doesn't need prior knowledge of which processes are going to be I/O bound. Whenever a promoted process is executed, its priority is demoted 1 level. Therefore, unless the process is again promoted due to an I/O completion, its priority will tend to fall back to the initial or base level. And finally, no normal process can be promoted beyond priority 15. That is, a normal process cannot become time-critical via priority boosting. Nor can the priority be demoted below its base level. Thus, the essential difference between normal priority levels and time-critical levels is a fixed priority at the time-critical levels and a variable priority at the normal levels. Time-critical processes compete in a round-robin fashion within each priority level. Time-critical processes are not subject to time slicing. It's different with normal processes. A normal process may have variable priority due to priority boosting. In addition, a time quantum limits the execution time of all normal processes. Let's take a look at a simple example of scheduling under VMS by looking at 3 memory-resident processes. Process A monitors a robot on the manufacturing floor, periodically checking the robot's status. Because any malfunction of the robot will slow production, this is a time-critical activity. So real-time process A is assigned a priority in the time-critical range, say at priority level 20. Process B is an online inventory package. It's important that the system respond quickly to inventory queries. However, since the worst thing that can happen is that there would be a slight delay in responding to a query, Process B is given an intermediate priority of 4. And last, we have Process C, a batch process which computes the payroll. While payroll is undoubtedly important, it doesn't have to be done immediately. Let's say Process C is also assigned a priority level of 4. Initially, Process A, the process with the highest priority level, is in a wait state, awaiting a wake request to release it from hibernation. Processes B and C are computable. They are ready to take control of the processor. The scheduler awards control of the CPU to Process B because it is the memory-resident computable process with the highest priority. Process B executes, rather than Process C, because it is at the head of the queue. Now, someone wants to know how many widgets are available. Process B issues an I/O request and must wait for its completion before it can proceed. So it goes into a wait state and therefore surrenders the CPU. The scheduler again examines the memory-resident computable processes for the one with the highest priority. At this point, Process C is the only memory-resident computable process. The scheduler therefore awards control of the CPU to Process C, which begins to compute the payroll. A system event, a wake request for Process A, occurs. This causes the report system event code to execute. As a result of the code's execution, Process A becomes computable. RSE then requests the scheduler to be invoked because a process has become computable. The scheduler examines the priorities assigned to all the processes that are computable and assigns control of the CPU to Process A because it is the process with the highest priority. After a short time, the I/O operation Process B has been waiting for completes. As a result of this system event, the RSE code executes and determines that Process B is now computable. The RSE code also specifies the boost that can be applied by the scheduler to the base level priority of Process B. The scheduler is not invoked because Process A still has the highest priority level, so Process A continues to control the CPU. Process A completes its work and is sent into hibernation again. The scheduler checks priority levels again and gives control of the CPU to Process B, which has had its priority level boosted. As soon as Process B is scheduled, its priority is reduced by 1. The scheduler does this to allow a process that has received a priority boost to begin to return to its base priority. Process B executes until the end of its quantum. Since it remains the computable process with the highest priority level, the scheduler allows Process B to retain control of the CPU until its time quantum expires or until it issues an I/O request. This example gives you an idea how processes are scheduled. Now, let's refine our view of scheduling in queues. You have seen that there are 32 queues for those processes that are memory resident and computable. These queues are used by the scheduler to determine which process executes next. In addition, there are queues for computable processes which are not resident in memory. These processes have been swapped out to disk storage. In the next unit, you'll see these queues are used by the swapper. It's actually misleading to say that processes are placed in the queues we've just discussed. It's more appropriate to say that software process control blocks reside in queues. To much of VMS, the software PCB is the process, because it exists in memory for the life of the process. As discussed in the last unit, the software PCB contains the information which is essential to determining whether a process is swapped into memory. Now we'll describe some of the information related to scheduling which is included in the software PCB. State queue links connect the PCB to other PCBs in the same queue. One link points forward to the next PCB toward the head of the queue, and the other link points back to the next PCB toward the end of the queue. The priority is a numerical value associated with the process. As we've seen, the priority level is a major factor in when the process is scheduled. The address of the hardware PCB is included in the software PCB. This address is used to load the register values when a new process takes control of the CPU. The process state specifies the particular queue to which the PCB belongs. For information on the remaining parts of the software PCB, see the section on the software PCB in Lesson 1 of your course reference guide. As events occur for a process, the software PCB is moved between queues to reflect the state of the process. A change in process state often causes the scheduler to re-examine which process should be executing. For example, a process that completes a terminal input operation changes from a local event flag wait state to the computable state, and thus would be eligible for execution. The scheduler interrupts the execution of a process when it determines a new process should take control of the CPU. To accomplish this, the scheduler performs a context switch. A context switch is simply an exchange of the hardware context of two processes. The hardware PCB is the data structure which represents the hardware context of a process. When the execution of the current process is interrupted by the scheduler, a save of the hardware context to the appropriate hardware PCB must occur. You'll recall that the hardware PCB stores the contents of the processor's registers. The system obtains the address of the hardware PCB from a special register. Without this address, the system wouldn't know the location of the PCB. The scheduler then executes a save instruction, which saves the register values of the interrupted process to the hardware PCB. The scheduler is now ready to establish the hardware context of the new process. The software PCB of the new process contains the address of the hardware PCB. VMS transfers control to the new process by loading the address into the appropriate special register in the CPU. Because the scheduler now knows where to locate the hardware context of the new process, it can execute instructions to load the hardware context to the processor registers. When these instructions have been executed, the context switch is complete. So whenever the execution of one process is interrupted and another process begins execution, a context switch occurs. A save of the contents of the CPU's registers occurs, followed by a load of the hardware context of the new process. In this unit, we've seen that VMS schedules processes based on process state and priority. Only processes in a memory-resident computable state can gain control of the CPU. Processes at time-critical priority levels are most likely to have their processing requirements met because processes with the highest priorities are given preference in scheduling. All processes at the same priority level are scheduled on a round-robin basis. As long as a real-time process remains computable, it runs until it is preempted by a higher priority process. Normal processes, those used by most interactive and batch users, are scheduled on a modified round-robin basis. VMS attempts to provide equitable service to normal processes by boosting priorities of processes in a way that favors highly interactive processes, and by using time quanta to preempt long-running jobs. When a process is preempted, a save of its hardware context to a system data structure called the hardware PCB occurs. The hardware context of the new process then loads to the CPU registers. This context switch allows the process which lost control of the CPU to resume later. All this is done in a way that is transparent to the user. This completes Unit 6. Before starting the next unit, please review the material and complete the exercises in your course reference guide.